Torque on a magnetic dipole when placed in a uniform magnetic field. Okay, if you remember in chapter 3, okay, sorry, I think it's chapter 2, it's chapter 1, sorry, yeah, it's chapter 1. When an electric dipole is placed in a uniform electric field, then the electric dipole will experience, a torque, which means the dipole will rotate in a, in the electric field. So similarly, when a magnetic dipole is placed in a uniform magnetic field, let's say this field is acting along the plane of the paper, and this field, let's say it has got a strength capital B. Okay, now this is my magnetic dipole, which consists of two poles, south pole and north pole, right, separated by a distance 2L. Now I place this dipole, let's say at an angle theta with respect to the magnetic field. Okay, now the south pole and the north pole of this magnetic dipole, they will experience a force. The force experienced by the south pole will be minus QMB. The force experienced by the north pole will be plus QMB. So it is seen here that, the magnitude of the two forces are equal, but they are opposite in direction. So therefore, when two forces, right, it seems like two forces are acting at the two ends of the line, then the line will rotate. And this rotation, right, it will be in clockwise direction. So because the line rotates here, so I can say there is a torque, because torque is a rotating force, and this torque, right, it is represented by this letter or this symbol tau, which is a Greek symbol, and we define tau as either force times the perpendicular distance between them, or tau is equals to, when I say either force, you can take either minus QMB or plus QMB, but only the magnitude. So when you see only magnitude, it is QMB only. And what is the perpendicular distance between them? Now the perpendicular distance between the two forces, it is like this. Okay, look. Okay, this is north pole, this is south pole. If you drop a line, if you extend this line backward and drop a perpendicular in this way, then this angle is theta. Let me name this as a point, what point I shall name? Let's say this is point M. Okay, now this is 2L. So if we take sine theta from here, then sine theta, it is equals to how much? Nm by ns. Nm by ns. Or just Nm is equals to ns sine theta, or Nm is equals to, what is ns? Ns is equals to 2L sine theta. Now this Nm, it is actually, the perpendicular distance between this force and this force. So instead of perpendicular distance, I will write, okay, here it is Nm, which means QMB times the perpendicular distance is how much? 2L sine theta. Okay, or you can say this is QM times 2L and then B sine theta. Or tau is equals to, now what is this? QM into 2L. Product of either charge and the distance between them, product of either poles and the distance between them, that is magnetic dipole moment, which is small m. So instead of this, I'll write small m and then B sine theta. Okay, so when I say MB sine theta, right, this is just the magnitude. Okay, this is the magnitude of the torque, right? So if you express this torque, in vector form, then I will write tau arrow is equals to m arrow cross b arrow. Alright. Okay, because we know AB sine theta, is equals to how much? A cross B. Okay, so similarly, MB sine theta, it can be written as M arrow cross B arrow. So because this torque here, it is a vector quantity, so its direction here, it should be perpendicular to the plane containing both M arrow and B arrow. Okay, where is M arrow? M, it is actually, right, acting from south pole to north pole. This is the directions of small m. Where is the directions of B? Directions of B is like this. Okay, now this tau, it should be acting in this way, perpendicular to this plane. Suppose like this. This is small m, this is B, then your tau will be acting in this way. Right. Okay. Right. Or this can be found, by using the Fleming right hand rule. That means if you rotate your right fingers, okay, stretch your fingers right in this way, and if you rotate all these four fingers in this way, that means you are going from M to B, like this way. So this thumb, okay, this thumb which is acting inward, perpendicular to the board, that will give you the directions of tau, or the directions of the torque which is acting in on a dipole. Okay, now I'll name this as my equation 2, which is the vector form. Alright, so after this we will see about special cases. The first case is when theta is equals to 0 degree, what will happen to tau? When theta is 0, then sine 0 is 0. So 0 times mb will be 0. Similarly, when theta is equals to 180 degree, tau is equals to how much? Sine 180 is 0. 0 into mb will be 0. And case number 3 is when theta is equals to 90 degree, tau is how much? Sine 90 is 1, so 1 times mb will be mb. And because this is being non-zero, so we call this value as a maximum value. Alright, so here it means that in the first two cases, when theta is equals to 0 degree, it means that this dipole, it is acting in this way, or it is held parallel with the magnetic field. When it is 180 degree, it means this dipole, the south pole, it is this side. So the south pole, it is like this, South pole, this is north pole. It is acting anti-parallel to the field. So when the dipole, okay, it is placed parallel or anti-parallel to the magnetic field, then that dipole will not experience any torque, because we have seen here tau is equals to 0. But in the third case, we notice that when theta is 90 degree, tau is maximum, which means when this dipole, it is held perpendicular to the magnetic field, then this dipole will experience what? A maximum torque. That means it will experience, a rotating force. So that means this dipole, when held in this way, it will move, it will rotate till it becomes parallel to the magnetic field. Okay, so these are the special cases of torque experienced by a magnetic dipole placed in a uniform magnetic field B.